So we're kind of coming in close to a landing with this set of lectures. And the one of the last few reactions I want to take a look at is known as epoxidation. And I'm going to combine this with the reaction on the next page, kind of as like a step one, step two sequence. But let's just talk about what an epoxide is and how we make them. So an epoxidation reaction is the formation of an epoxide which has this structure. It's a three-membered ring with oxygen as one of the members. So it's like a cyclic ether, but it's a three-membered ring ether from alkenes. Now, the most common way that this is made, we'll start with an alkene, and the other compound that we make or that we use is called a peroxy acid. Now, peroxy acid looks a little bit like a carboxylic acid. It's just got an extra oxygen in there. So remember back from GChem that oxygen-oxygen single bond is, we call it a peroxide. And that's why we call this a peroxy acid. It's like a carboxylic acid, but it's got a peroxide bond in it. And this forms an epoxide. Now that oxygen can be going up or down. In this case, it doesn't matter because this is a meso compound, but just keep that in mind that I could have as easily written the oxygen going downwards. Now, one of the most common peroxy acids that is used is known as MCPBA, and that stands for metachloroperoxybenzoic acid. And here's the structure of it. I'd like you to know the acronym, know the structure as well. Sometimes you might see this functional group here abbreviated like this, R, and then you'll see CO3H. So CO3H is like our shorthand for peroxy acid. And a lot of times you'll see me use R as like just a generic chain of carbons. But this is the most commonly used one simply because it's really cheap, it's pretty stable, and it's a solid, so it's easy to weigh out and measure. All right, and let's take a look at the mechanism for epoxidation. So I'm going to draw the peroxy acid in this way. And I'm using R here just to um, um, really make it like shorthand. And so this is a concerted addition of that oxygen. And this is the oxygen here that's going to get added to the to the alkene. So our first step, or not really step, but our first arrow we'll draw here. Our next arrow, we'll use these pi electrons to make a bond to the oxygen. And then I'll use a different color here. These will go here. And then I'll use one more color here. We'll use those pi electrons to make a bond to that hydrogen. So again, this is concerted, meaning we do this all at once. So what does the result of that look like? So I'll use blue here to represent the result of that blue arrow forming a bond. And then we have an oxygen, the red arrow will make that bond. And then as the side product, here is purple arrow making a bond to that hydrogen. And then we use orange for the new pi bond here. All right, but the thing I want you to focus on the most is making the epoxide. Now, one of the most common things that we do with epoxides, and I will say this, I want you to know this for right now. We will come back and talk about more ways to make epoxides later. Um, and we could do a whole variety of things with them. But one of the most common things we're going to do is add water to the epoxide. And this does what's called an anti-dihydroxylation. Or basically what this means is adding two OHs anti to each other. The way that we do that is through an epoxide. So a lot of times this starts with an alkene. We'll do an epoxidation. So this will be like step one. And then we add some dilute acid. So this is acid catalyzed. And what I want you to do is think about hydronium as H2O, H plus. And it will add another OH group in an anti-fashion. And you do get it's an enantiomer, depending on which side that OH decides to, the water decides to attack. So let's look at the mechanism for this. It's acid catalyzed, so the first thing we're going to do is protonate that oxygen, the oxygen of the epoxide. Now, what that's going to do is, I mean, the epoxide ring is already highly strained, so very reactive. Now, I've protonated that oxygen. It's going to make these carbons even more likely to be attacked because we're going to kind of treat this as a leaving group. And so water is going to come along here and attack one side of the epoxide. And let me ask you this again. If that epoxide ring is going upwards, what direction do you think the water is going to come in from? It's going to come in from the opposite direction. And then water doesn't like being positive. I'm sorry, oxygen doesn't like being positive. So we'll deprotonate that. And that's how we get to this product. We can show getting to the other product by having water attack the other carbon. So let's kind of put all this in one big summary. By starting with an alkene, and then by first reacting it with a peroxy acid, it will make an epoxide. In the second step, we add acid, and that results in an anti-dihydroxylation. Again, notice how kind of similar this is to some of the other reactions that involve these three-membered ring intermediates. The nucleophile is always going to come from the opposite direction. Now, one of the cool things is that we can switch out that water in the second step with an alcohol. So if we use, say, ethanol and an acid catalyst, then we get an OH and an ether anti to each other. And we get it's an enantiomer as well. So depending on what our nucleophile is here, we can either make, do a dihydroxylation to get two alcohols, or we can get an alcohol and an ether adding across that alkene.